All right, let's get back here after doing that example. Let's shift gears to looking at open systems. So if you recall here, let me take a moment to remind you the distinction between open and closed systems. So closed system, so remember a closed system was a fixed quantity of mass So the picture here is we got some sort of mass M, and it's undergoing some sort of heat or work interactions, and it's going to some final state, okay? So we have a fixed quantity of mass, whether that's a piston cylinder device containing a gas, or a rigid container containing a saturated mixture or a mixture. So a fixed quantity of mass is a closed system. Remember, open systems, so a fixed, a given region in space, a given region in space. So the idea here is we need not have a fixed quantity of mass. For example, let's say we have, I don't know, a power plant. So let's see here. Here's our power plant. And so here's our smokestack. So here's our power plant. So coal or natural gas, whatever is your preference. Coal comes in one end, air comes in the other, and products of combustion come out the top. If my region in space is the coal plant, then I have mass crossing the system boundary on three different places. I have mass crossing the system boundary for the coal being supplied, the air being supplied, so that's two, and then mass being ejected from the system at the products of combustion at the top of the smokestack, okay? So this is an example of an open system. It's a fixed region in space in which mass is crossing the system boundaries, okay? Two completely different kinds of systems. A fixed quantity of mass, there's no mass crossing the system boundary. So if this is my system, no mass crossing the system boundary, maybe there's work and heat, but no mass. And then my open system, I do have mass crossing the system boundary. And I can also have work and heat going on as well, okay? A given region in space, nothing about fixed mass or no mass crossing the system boundary. Here we have mass crossing the system boundary, okay? So how do we go from equations which are valid for closed systems to equations which are valid for open systems? That's what we're going to be talking about for the next half an hour or so, all right? First of all, let's list the closed system conservation equations, okay? Let's list them. We have conservation of energy. So E, balance, or the conservation of energy. By the way, I'm going to write it on a rate base with the dots in there. So we have Q dot minus W dot is equal to dE dt. And I'm going to write here and specify that this is for a closed system. The change in energy over time for a closed system. I'm going to specify that we're talking about the energy of a closed system. There's also a mass balance. We haven't talked about it much. Why? Because it's kind of trivial. So mass balance. The change in mass over time for a closed system, what's the time rate of change of mass in a closed system? Remember, a closed system contains a fixed quantity or a constant quantity of mass. It's a fixed quantity of mass. So what's this time rate of change? What's the time rate of change for the mass of a closed system with constant fixed mass? Well, it's equal to 0. Okay, it's equal to 0. All right. So those are our energy and our mass balances for a closed system. Now I'm going to rewrite these two equations in a rather strange way at first, but it's going to help you later on. So I'm going to make a table here. Going to make a little table here. Let me make sure I get it set up properly. Okay. Now I'm going to have a couple of columns here. The first thing I'm going to write here is extensive property. Extensive property. Remember, extensive properties depend on the extent or size of the system. Mass and energy are extensive properties. Energy and mass depend on the size of the system. So I'm going to write here energy E and mass M. Okay, these are our two extensive properties that we're dealing with these two conservation equations, energy and mass. Okay, so let's do that. Now over here, I'm going to write beta, the Greek letter beta. Beta is going to represent algebraically my extensive property. So right here, I'm going to write beta equals E. So beta is just a variable that represents my extensive property. In the first row, it's going to be energy. And in the second row, it's going to be mass. Okay? On the next column, I'm going to write beta per unit mass. Little b, lowercase b, which is beta, my extensive property, per unit mass. So beta divided by mass. So B is going to be energy in the first row divided by mass. What's energy per unit mass? It's specific energy. This is total energy we're talking about. So this is lowercase e. All right? That doesn't look like an E. And in the case of mass, lowercase b is mass per unit mass, so beta per unit mass. These cancel out and I get 1. Okay? So I've got two extensive properties with conservation equations, energy and mass. I've listed them here, mass and energy. I've introduced a quantity called beta, which is going to be my extensive property. Energy in the first row, mass in the second row. And then I have a beta per unit mass, which is a lowercase b. And that's going to be energy per unit mass, lowercase e, mass per unit mass. They cancel out and you get 1 for the property mass. Now let me write down my balance equations, my energy and my mass balance equation in terms of the properties beta here. Okay? My generic variable, extensive variable beta, or property beta. Let's see here. So I have Q minus W dot. And instead of writing dE dt for the closed system, I'm going to write d beta because beta is equal to total energy, d beta dt, and this is for a closed system. Closed system, all right? So for energy, the conservation equation. Conservation equation. Conservation of energy is Q minus W dot is equal to d beta dt for the closed system. I'm just rewriting the energy balance for a closed system in terms of beta. For mass, I get d beta dt for a closed system is equal to 0. That's mass conservation right there. All right? That's mass conservation. You can also write it like this, maybe to get it to look a little bit more like the energy conservation equation. I'm going to flip it. I'm going to put a 0 over here and a d beta dt on the right-hand side, just so that the d beta dt terms are on the same side of the equation. 0 is d beta dt for a closed system. Okay? All right, so I've rewritten the energy and the mass balance for a closed system in terms of a generic property, beta. Beta can take on any extensive property, energy, mass, and then I have specific beta or lowercase b here as well, okay? Now we're gonna use this rendering or re-expression of the conservation equations along with the Reynolds transport theorem, which we're going to develop in just a moment, to create open system energy and mass balance equations. Okay? So have this written down in your notes because we're going to be coming back to it later.